Hello, welcome to our video solution to problem 13 from Superquiz 2, another optional problem looking at relations, functions, injectivity, surjectivity again. Here we're trying to apply the definitions that we talked about in problem 12 to a couple of explicit examples. So in this first example, notice here, by the way, these are relations from a set S, which is just the numbers 1 through 5, to itself. So each one of these needs to be a subset, right, of S cross S. Okay, so each relation is a subset of S cross S. So that means pairs, right? So this is all things of the form, you have some S, and maybe let's call it an S prime, such that S and S prime are in S. Okay, so that's why we have these pairs here. Now, in order to have a function, we saw in the last video that for each input, right, that is for each element of the domain, there must exist a unique element of the codomain such that you have a pair in the relation. So we have 5 different elements in the domain, and so to have a function, we're going to need to have exactly 5 elements in the relation. Well, if you look at this first one, R, we have 1, 2, 3, 4 elements, not 5. What went wrong? Well, in the first component, we have 1, 2, 3, and 4. There's no 5. Okay, so this violates the definition of the function. So R is not a function since there is no S in S such that 5 comma S is in R. Okay, we have an element 5 in the domain. We need there to exist a unique element in S such that 5 comma S is in R, and there isn't one. Okay, so it's not a function. How about injective? Well, injectivity is going to require us to show that for each element in the codomain, okay, well, that's also S, so 1, 2, 3, 4, 5, there's at least, or excuse me, there's at most one element in the domain which maps to it. So we take a look here and let's see, 3, 4, 5, 5. Oh, look at that. 5 appears twice in the second component. So you have one element in the codomain, 5, and 2 different elements. Oh, sorry, we're in the wrong one, aren't we? We're in S. Let's look at R again. My apologies. 1, 5, 4, 2. Okay, they're all different. Okay, so each of the numbers, 1, 2, 3, 4, 5, viewed in the second position, has only one element corresponding to it in the domain. So R is injective. Okay, how about surjective? So for surjective, for each element in the codomain, which is again 1, 2, 3, 4, 5, there must be an element in the domain which maps to it. Well, let's see. 1, 2, and there's no 3. So R is not surjective since there is no S in S such that S comma 3 is an element of R. Okay, so again, to be surjective, for each element in the codomain, right, in the second position here, we need to be able to find something to put in the first position, which will be in this relation R. And there is nothing with a 3 in the second position. Okay, so R is not a function, it is injective, and it's not surjective. All right, the same type of reasoning is going to apply in all these other situations, so we'll go a little bit faster. So how about S? Is first S a function? Well, we know to be a function, for each element in the domain, and there's 5 of them, there must be a unique element in the codomain corresponding. So there can only be 5 terms. 1, 2, 3, 4, 5, 6. Oh, there's 6. Where's the problem? Let's see. 1, 2, 2. There are 2 different pairs that have 2 in the first component. That's not allowed. So 2, 4 and 2, 5 are both in S. Okay, this is like a curly S here. Funny S. So this implies S is not a function. All right, is it injective? Well, let's see here. We need to look at the second components. 3, 4, 5, 5. Oh, there's two 5s here. So we have two different inputs, 2 and 3, which would get mapped to the same output, right? 5 has two different preimages. All right, so we have 2, 5 and 3, 5 are in S, and that implies S is not injective. Okay, how about surjective? Well, let's see. We're looking for 1, 2, 3, 4, 5. Hey, we got everything, right? Every element is mapped to. Okay, so S is surjective since every element of S has a preimage. Cool. All right, so S is not a function, it's not injective, but it is surjective. How about T? So again, we're going to check 1, 2, 3, 4, 5. Okay, that's a good start. Now let's see. Does each element appear over here on the left? 1, 2, 3, 4, 5. Absolutely. So it does nothing appears twice, and all of them appear. So T is a function. Okay, so I'll say T is a function. How about injectivity? Well, we have to check all of the outputs and see if they get mapped to more than once. Well, 1, 2, 3, 4, 5. Hey, everything's only mapped to once. All right, so T is injective since every element, let's just abbreviate that, every element of S has, in this case, exactly one preimage. And actually, once we know every element has exactly one, we also know it's surjective, because surjective meant that it has at least one. Okay, so we could actually add in here, it's injective and surjective. In fact, this means that this T here is a bijection. Okay, what's the last one? U. So let's check again here. So we have 1, 2, 3, 4, 5. So every element is sent to exactly 1. So U is a function since every element of S has exactly one image. Okay, how about injectivity? Let's check. 1, 2, 3, 4. Oh, 4. Ah, look at that. 4 has two preimages, 1 and 4. So U is not injective since 1, 4 and 4, 4 are elements of U. Okay, so 4 has two preimages. How about surjective? Well, we got to make sure every element in S has a preimage. So 1, 2, 3, 4, there's no 5. So U is not surjective since, okay, we could use the same language as we had up here, or we could say since 5 has no preimage. Okay, so it's another way to write it. Okay, so this means i.e. There is no S in S such that S, comma 5 is an element of U. Okay, so it just takes a little bit of practice using these definitions. I like actually this way of writing relations in terms of pairs just because it's so easy to break it up in terms of the left component or the right component. But of course, you want to be able to translate this into the normal function notation, the f of s equals t notation. But that's, again, just going to take some practice. All right, good luck.